Hello all, I welcome you all to the 15th lecture in this course, EE614. The last time we met, we thought of proceeding towards BJT. We saw about nonlinear behavior in PN junction diode, and we discussed about charge dynamics and such. But before we proceed to do some serious BJT device physics and characteristics, I thought it would be a good diversion to study metal semiconductor junctions. It will also help you to ramp up to the actual discussions which precedes BJT discussions. Okay, so let us have about 2 lectures on this metal semiconductor junctions. We will talk about Schottky barrier, we will talk about ohmic contacts, current in these junctions, and this is very important in most of 3-terminal devices, particularly BJT and MOSFET, that we are going to talk very soon. Right. So the topic of today's discussion will be metal semiconductor contacts. Okay, so before we go into the actual discussion, there are a few things which needs to be discussed in terms, like there are few terms which we will see which we did not fully define last time. The first one being what is called as the vacuum energy level of an electron. So basically this is the energy level of an electron which is not in an atom. Electron not inside an atom, and this is the highest energy level in the entire system that we are going to discuss, and it's a reference. It is a reference and the highest energy level. Now, why does it have to be the highest? You would have seen several band structures where I think you must have come across this before. So we draw the metal Fermi level somewhere like this, right? And draw the vacuum level at very high energies, which is, let's say, E0. The reason why the vacuum energy level is so high is that you need to spend energy to push an electron from the atom to the vacuum level. You need to spend energy or supply energy to the atom to free an electron. Another way to look at it is, if the vacuum level is lower than the Fermi level of the atom, let us say for hypothetical purposes, if we have E0 like this, the entire system wants to lower its energy, right? So the electron from the Fermi level will just jump to the vacuum, thereby reducing the overall system energy. That's where every system tends to go spontaneously, right? So the atom will just degrade, right? So that's the reason why the vacuum level is typically much higher than what we than every energy level that we discuss generally. Okay, so in this, there is the energy that you have to spend to take an electron from the Fermi level to the vacuum level is called as the work function. So it is Q times psi m. Psi m is the actual work function, and charge times the potential is the energy, right? So this we have seen before. So the actual potential is psi m is the work function. So psi m is the work function or potential difference between the vacuum level and the Fermi level. Psi m means for metal, psi s is the work function for semiconductor. We will very soon see why this does not really make any sense, because most of the time the work function or the Fermi level in a semiconductor lies in the forbidden energy gap, right? So you typically do not have any density of states at the Fermi level, so you do not take an electron from the Fermi level and take it to the vacuum, right? So psi s is typically an hypothetical number. We won't deal with psi s mostly. What we deal with is called chi, which is electron affinity. It is the same thing. Basically, it is the change in the energy when an electron is added to a neutral atom. So what it means is, let us take that if we have a semiconductor, some Fermi level somewhere, and then some vacuum level EC, E0, right? This is EC, this is EV, this is EF. We have seen this before. The change in energy when an electron is added to a neutral atom. So this atom is neutral right now. You have doped it and you have enough number of carriers and such. As such, it is neutral. If I add an electron to the conduction band, that's where you typically add an electron to, because at zero, let's say at 0 Kelvin, most of the valence bands is full. The only place where you can add an electron is the conduction band, right? So you add a conduction band, and the energy from vacuum to this is the electron affinity, is chi, right? And let us take the energy separation between the conduction band and the Fermi level to be chi, to be psi n. This is some notation that we will use pretty soon, right? So now let us compare these two together. Let us take okay, so our exercise today is to see what happens when I join this metal and the semiconductor, right? So as we have seen in the previous case, in our PN junction treatment, there will be charge transfer between the two if there is a difference in the Fermi level. So we will go through these things one by one. Typical metal work functions, so Q psi m's typically ranges from about 4 to 6 electron volts, right? Typical psi, it turns out to be something around 3 to 2 to 3, depending upon the semiconductors, something in this range, right? So what it means is, if it is an n-type or typical semiconductors, you have a let us draw the relative orientations between these materials. On the left, I am drawing the metal work function. This is EF. I have the vacuum energy level. The vacuum energy level is something which is constant, which remains flat at equilibrium, right? Because it should be the same energy that is required to push out, right? So this is E0 and this is Q psi m, and you have EC, EV, EF, and this is Q chi, electron affinity, as we saw, and this is Q psi m, sorry, psi yes, and this is psi n, Q psi. So Q times any of these psi, chi are all potentials, and Q times that will give you the energy, right? So now the question is, what happens when I join these two together? So obviously you see we are taking a situation where you have the Fermi level of the semiconductor higher, relatively higher in comparison to the Fermi level of the metal, right? So what it means is you have higher probability of electrons in the Fermi level, in the semiconductor Fermi level in comparison to the Fermi level of the metal, right? So, but then when you join together, the Fermi levels should align, as in any semiconductor thing that we have studied. And when we join these two together, there are a few things that we have to keep in mind, right? The first thing is the electron affinity band structure, band gap, intrinsic levels, right? They are all material parameters. And they remain constant. So what it means is this chi s remains constant. The energy difference between the vacuum level and the conduction band remains constant at all places in the semiconductor, irrespective of its proximity to a metal or a semiconductor. So this is true because of the fact that so chi s is the energy difference from vacuum to a semiconductor, right? It does not depend upon the polarity of charges in the semiconductor. Does not depend upon how many carriers the semiconductor has at that point and such. So it is generally defined as a material parameter, like the band gap. There can be some minor differences depending upon the temperature and the current occupancy of levels, but for first order treatment, we are just taking it to be constant for all for the material itself, right? So with this given, let us consider the situation where I join these two together, right? So if I make an interface like this, obviously you have electrons moving from the semiconductor to the metal, right? So basically an electron here would like to jump from here to here. Why? Because in the metal obviously has lower energy, and you have a lot of vacant states in the vicinity of the Fermi level in the metal, and you have occupancy in the semiconductor at higher energy levels. So total energies, the system would want to go to lower energy level, and hence the electron will jump from the conduction band in the semiconductor to the Fermi level and of the metal till the Fermi levels match. So Fermi levels will determine what is the occupation probability, and after when it matches, the number of electrons going from right to left will equal the number of electrons which go from left to right, and hence you get a steady state situation, right? So now let us look at the steady state situation. The first criteria is the Fermi levels should line up, right? It will all come to the same state. So you have a metal here, EF, right? And the metal work function does not change. Q psi, right? On the semiconductor side, you have the electron close to the interface move out to the metal, right? So basically you are forming a depletion region somewhere close to the interface. Because you have formed a depletion region, as we have seen in PN junction, there should be a gradation in the conduction band, right? So this will happen because it has to move away from the Fermi level at this point, because the number of electrons have reduced here, and there is certain region till which the depletion width proceeds. After that, the band structure do not have any gradient, meaning that there are no potentials. It is in this width you have a depletion width, you have a potential, you have an electric field, everything within this area, right? We have seen these things before in the semiconductor as well, in the PN junction interface as well. And we right now discuss that it has a chi which is constant and which is a material parameter, right? And because there is a slope in the conduction band, your chi should also have a slope. The vacuum level here also has a slope, right? So you have q psi, mean q psi everywhere, q chi everywhere, right? So from these, so and you have a discontinuity in the band structure here. So you have the Fermi level here, EC is here, and you represent, so basically an electron in the metal, if it wants to go to the semiconductor, it has to cross this barrier. So let's say an electron here, right, it has to cross this barrier height, and this barrier height, written as psi b, small b, is just q psi b is just q psi m minus q chi, right? From this diagram, this is true because your chi is a material parameter and it is constant. So at the interface also it has to be chi, and the metal work function does not change, right? So your actual Schottky barrier, so this is what is called a Schottky barrier, is an intrinsic material parameter depending only upon the metal work function and the electron affinity in the first order treatment that we have currently seen, right? So with this, let us go and study what happens to the charge, what happens to the potential and all those things. So there can be a few things which we already see, right? Let us take this to be the depletion width WD, and if we draw the charge distribution in this particular stuff, right, the metal has actually taken electrons, and because metal density of states is very high, we have seen this before, at the interface we have a very sharp charge density which is negative, which we saw, and depending upon the charge density or the doping density in the semiconductor, we will have some depletion with QD, and we took it as an n-type semiconductor, so we will have a doping density Nd here, right? So you have some positive charges because the electrons have moved to the other side, right? So now let us once again solve the Poisson's equation that we saw before, and then have a feel for what is the interface potential or the built-in potential we will have for this simple abrupt junction Schottky diode. So this a metal semiconductor junction is typically called as a Schottky diode. So it is just a very simple situation, right? So let us write the Poisson's equation. We will do it once again just to have just to refresh our memory about our PN junction Poisson's treatment that we previously had. Okay, I could have skipped this, but just for the sake of clarity and so that I just want to go slow, right? So let us do the Poisson's equation at both places, like what we did in the PN junction side. Let's call this at x is equal to 0, and we typically write this Poisson's equation at two different places, right? So let us do it at x greater than 0. The Poisson's equation is written like this: minus d square psi bi. Psi bi is what I write as built-in. Psi b is the barrier, bi is the built-in. Dx square is basically dE by dx is rho by epsilon, right? This is what we have seen, epsilon s as a semiconductor, and this rho we know we can write as q by epsilon once again by nd plus, right, minus n plus holes plus na minus, and all of these things are very small in comparison to the nd, and we have taken it to be an abrupt junction, so it is all going to be spatially independent, right? So under these situations we can write E of x is just an integral of this, so you will get q by epsilon nd x plus some constant, right? Now we have to find what happens at x is equal to 0, what is the field at x is equal to 0, right? And we have taken the depletion width to be d, so what is the positive charge density? per centimeter square. So basically the charge neutrality will give you that your rho at x lesser than 0 should be equal to rho at x greater than 0, which will turn out to be q nd wd, right? That is the rho right hand side. So the rho left hand side should be same, but it should be minus q nd wd, right? And if this is the actual density here, and this is point charge density, so E at x is equal to 0 is E max, which we know to be minus q nd wd by epsilon s. And if we have something like this, we can write our electric field as q nd x by epsilon minus q nd wd by epsilon s, and we can write our built-in potential again as another integral of the same thing, which will turn out to be minus q nd by epsilon s wd x minus x square by 2. And we know how this one will look, right? So if I plot this, the electric field will look like this is at x is equal to 0, right? So minus em, this is wd, right? And the potential, sorry, this should be plus, and the potential will be so once we have this relationship, we can write at x is equal to wd, your actual psi bi of x, right? So psi bi is equal to v naught will turn out to be q nd by epsilon s wd square by 2, and actual width of the depletion width will turn out to be 2 epsilon s v naught by q nd. And so basically this is the width, and this is very similar to what we saw before, right, in the p-n junction. Now we can add a few more to this depending upon the bias potentials, right? So basically we take the same metal semiconductor contact and then apply some potential V, and depending upon this V, if V is greater than 0, you have forward bias, right? And if we have a forward bias, then WD will turn out to be, actually is other way around, right? Because we have taken the semiconductor to be M, so V lesser than 0 will be the actual forward bias. No, sorry. Okay, so minus plus, so V greater than 0 will be the forward bias. Anyways, so let's continue. So with this, W, the width of the depletion will be 2 epsilon s by q nd V naught minus V, which is applied bias, minus kt by q. And we know from where this kt by q comes. Kt by q comes as an as the right solution, because we have neglected the approximations. I mean, we have made an approximation that n and p are much smaller than nd. So if you also account for some minority carriers, some mobile charges in the depletion width, you get this kt by q, which is what we saw in the sorry, this will turn out to be root of, this is what we saw in the p-n junction treatment as well. So with, if this is the width, then the maximum electric field will be root 2 q nd by epsilon s v naught minus v minus kt by q. And the depletion capacitance CD is width of the depletion width by epsilon s. This is what we saw before, and this will turn out to be root 2 epsilon s nd by 2 v naught minus v minus kt by q. Right? And 1 by CD square is 2 v naught minus v minus kt by q by q epsilon s nd, and basically nd will turn out to be minus 2 by q epsilon s 1 by d square 1 by cd square by dv. It's not d square, just d. Right? So basically what it means is, if I take the depletion width or depletion capacitance as a function of applied bias V, and then plot it as a function of or do 1 by CD square and plot it as a function of potential, the intercept or the slope will give me what is the doping density. And this is mostly done in the places where you have differential doping, or in situations where you have ion implantation at a particular depth and all those things. So typically this is what is done even in the Schottky diode situation, and this is very similar to what we saw in the PN junction that we saw sometime before, right? So let us to just summarize, the barrier potential psi b is a material parameter and depends only on the metal work function and the semiconductor affinity. In the first order treatment that we saw till now. Right? So now let us go and then take a look at some other aspects where your psi b could be changed for the same metal semiconductor combination. Right? The first thing would be image force lowering. Or it's called the Schottky barrier lowering. The origin of this particular behavior is, if I take a metal sheet, right, and then I move an electronic charge in proximity to this, so this metal sheet, if it is maintained at a constant potential V, you will get a positive charge induced in this metal sheet due to this negative charge here, right, because of the dipole action, right? And this positive charge distributed in this entire infinite metallic sheet, and the presents a force which acts on this particular negative charge, pulling it closer, right? This is the force which the distributed positive charge presents to this electronic chip. To calculate this particular force, you use what is called as an image force method, where this distributed electric charge is considered to be like another charge equal and opposite to the charge presented previously, with the same distance from this metallic change, right? If this is x, this is also x, right? So the force that this negative charge will experience because of the distributed positive charge can be represented by the Coulombic force between these two charges, the positive and negative charge, now separated not by x but by 2x. This is some basic electrostatic field tricks. I think you must have seen this in your undergrad at some point, right? So what happens? So basically this is very similar to what we will see very closely, right? So basically the force acting on this particular charge separated from this metallic sheet is minus q square by 4 pi epsilon 2x square, right? And the work done in moving this negative charge from infinity to x is f dx, which will turn out to be minus q square by 16 pi epsilon s, or epsilon naught actually, x, right? So till now we have been talking about an electron moving in vacuum close to the metallic sheet. Now what happens if if there is an electrical potential E, constant electrical potential E, right, once again in proximity to this metallic sheet? So what happens, instead of this force, which is spatially dependent, you have a force, an external force, which now is just minus q into E, because this E is a constant electric field that I have applied, right? And once again you can do the work done because of this external force, which will once again be minus integral to integral f of E dx, which will turn out to be minus q ex. So the total potential energy of this electron at any point x is summation of this Coulombic force because of the image charge minus q square by 16 pi epsilon naught x, and this because of the constant field that is present, right? So let us take an example of this metal sheet that we were discussing till now, and I have a Fermi level here, right? Some vacuum E naught, some work function q psi m. This was the ideal case, right? And this is the energy that is required to push an electron out of this, or it is the work done in taking an electron from the Fermi level of the metal to infinity. But right now that we saw that the work done in moving an electron from the metal sheet to any point x is not spatially independent as we seen here, but then it depends upon the space, right? And we saw it depends upon by 1 by x oddish, right? So the actual potential, instead of going directly to E naught like this instantaneously, it takes a while. So this is your ideal q psi m if you consider the image force charges. But then if you add to this the external field E, so this is at x is equal to 0, right? If I plot the image force charge here, it goes out something like this, and this minus QE, which goes like this, minus QE of x, right? So the actual summation of both of them will turn out to be, I'm going to draw this in some other color, which undergoes a maximum at x is equal to m, and there is a suppression of the work function, which is initially q psi m, to a value del psi, right? And this suppression basically turns out to be which happens at x is equal to xm, turns out to be root 2e proportional to the electric field, right? The more the electric field, the more the suppression that you get, 4 pi epsilon naught, which also turns out to be 2exm. We are not proving this, but then the suppression in the barrier that you can see, suppression in the metallic work function, due to the fact that you have an external potential in the proximity of the metal and the image charge effect, right, is a suppression of the work function from q psi m, which is the ideal value, to a q psi m minus del psi, right? But then right now we have just considered the metal work function suppression at vacuum, but when you have a metal interfacing with a semiconductor, there are other aspects to it, right? So in a metal semiconductor junction, you have the suppression del psi is smaller. Why? Because del psi is now 2e by 4 pi epsilon s, where epsilon s is the dielectric constant of the semiconductor, right? So because any force that is experienced is screened by the dielectric constant, so epsilon s for silicon is about 11.7, where epsilon naught is about 1, right? Basically epsilon r is equal to 1 for vacuum. So basically you have the lowering which is about an order of magnitude lower if you are working with silicon, right? Now the second thing is, in addition to the applied field, you always have some built-in potential. Therefore, your del psi depends on the applied field and the built-in potential. Right? So now let us quickly look at what happens at various applied potentials and what happens to the actual barrier height. Right? So now let us take the ideal situation where I have the metal Fermi level, I have the vacuum level, and I have the metal work function. And if I join it with a semiconductor, I have something like this, and this is q psi that we saw. This is E naught everywhere, right? Everywhere it is q psi, right? And we saw the actual barrier is q psi m minus q chi. This is the treatment that we saw till now, right? Now when there is image lowering and you have an external applied field, now the effect or the change in the metallic work function and hence the barrier height will look like this, right? So once again I have EF here, I have E naught here, and the ideal let us say this is q psi m, right? And the right, okay, so from this the actual you have what is called as right. So this is the case when you have V lesser than 0 and you have under reverse bias, and this is the case when you have V equal to 0 when external bias is 0, and this is the case when you have V greater than 0. Why is this like this? So basically you have a much larger barrier lowering at reverse biases. Why? Because the external field, the reduction in del psi, so basically this is del psi, and say this is okay, so this is del psi at V equal to 0, and this is del psi at V greater than 0, and the other one is del psi at V greater than or at V lesser than 0, right? So you have a much larger barrier lowering at reverse bias because you have a much bigger depletion width and a much bigger depletion potential at reverse biases, right? So when you have a larger reverse bias, you have a much larger barrier lowering and hence a much stronger injection efficiency from a metal to a semiconductor, right? So this is the story of image charge lowering of the barrier height. So finally, we will deal with interface states. Interface stage is another way in which the actual